And so at this time, I would like to introduce our first speaker. Our first speaker is Katiana DeYonke from UNC Chapel Hill, North Carolina in the United States. Please start sharing your screen.
Is that showing up for everybody?
I can see your slides and I can hear you.
Perfect. All right, well, hi, my name is Katiana DeYonke. I'm currently a senior at North Carolina State University, as well as a visiting scholar at the University of North Carolina at Chapel Hill. And today I'm going to be discussing privately owned groundwater wells that harbor cefotaxime-resistant enteric gram-negative bacteria with multidrug-resistant properties. So before I discuss research, it's important to understand why we should even care about antimicrobial resistance to begin with. Why is it important? So antimicrobial resistance, as I'll refer to as AMR, was declared a serious threat to global public health by the World Health Organization. And this is for reasons such as in the US alone, 2.8 million people were infected with an antibiotic-resistant infection, and there's an average of 35,000 deaths a year. This number just grows for the worldwide average of 700,000 deaths. There's also economic repercussions from antimicrobial resistance, one of which is a loss of global productivity. And it is averaged that in the next 30 years, there will be about $100 trillion lost due to antimicrobial resistance. So reasons such as these, you can see why the World Health Organization has created the One Health Initiative. And the One Health Initiative, as displayed by this graphic here, addresses antibiotic resistance and its flow between humans, the environment, and animals. So now going on to private wells, which we're specifically working with. Private wells aren't very well researched at all. There's not a lot of work done in groundwater research, especially in the United States. And there's more than 13 million households in the United States that do rely on private wells. And in North Carolina alone, 22% of North Carolinians use private wells. So the problem with this is that they're not regulated under the Safe Drinking Water Act, which means there's no regulations after the private wells are installed. There is a mandatory test when they're first installed, but other than that, it's completely up to the well users, and they're personally responsible for testing their own water, which is often not done on a regular basis. And this may harbor antibiotic-resistant bacteria. And if that antibiotic-resistant bacteria is pathogenic, that constitutes a potential public health risk. So this is a paper done by Amadei, and this is showing groundwater resources as a global reservoir for antimicrobial resistant bacteria. This is a systematic review showing the lack of research in this area. This is all global studies for the presence of AMR, and as in the table shown here, this paper condenses all of the research that's been done so far up to 2018 on this topic. And as you can see, there were only 70 listed in this paper as valid publications done on antimicrobial resistance, which is not a lot at all. And if you look down at the continent section of this table, you can see that it's broken down, and you can see that North America was involved in 4 of these studies, which again is extremely low. So specifically for our project, we had to figure out how the antibiotic-resistant bacteria gets into private wells to begin with. And there's quite a few different ways. So the first could be an extreme weather event. This is a precipitation map from Hurricane Florence, which hit North Carolina in October of 2018. Or just heavy precipitation in general could cause runoff or flooding, which could also affect private wells. Agricultural operations have their impact on private wells, as well as septic tanks that might just have an issue or a leak or aren't installed properly. They can have an effect on private wells, as well as the well itself. It could be compromised. As I said earlier, these wells aren't regulated after they're installed, so it's up to the personal well user to do that. And oftentimes they don't, and they are, out in the elements at any given time, sometimes only covered up by a tarp. So you can imagine that might not be the most sanitary way to take care of a private well, and therefore it will become compromised. So here's an overview of just the general process of the research we've done on antimicrobial resistance and what we did to look for the appearance of it. So first we went and got our samples. And once we had our samples, within the 30 to 48 hour period, we started pre-screening for antibiotic resistance. if we had any hits from that, we did a couple more tests just to confirm it. And then we would isolate a colony of that antibiotic-resistant bacteria, and we could freeze it. And that provided us a really flexible timeline to do whatever we wanted with the isolates. And what we did specifically to test for multi-drug resistance was run a few Kirby-Bauer tests. So for our sampling locations, we sampled at 3 different counties in North Carolina: Robeson County, Orange County, and Bladen County. And the results from all of these counties were pretty similar. There wasn't any huge discrepancy based on the county that we found. So this is how we processed our samples. So starting over with the raindrop, we started by sampling our samples directly from wellheads. And before we did this, we would use an alcohol-based sanitizer and also flush the spigot for about a minute to make sure there's no extra contaminants. And then once we had our samples, we would transport them in coolers with ice. And as soon as they were brought to the lab, they were restored in refrigerated conditions. Within the first 30 to 48 hours is when we performed the first set of membrane filtration. And for membrane filtration, it's basically a vacuum seal that when you pour your sample in, it's vacuum, like the vacuum pulls down, and anything left on a filter that's placed in between the vacuum seal and the liquid, when it's pushed through there, any type of bacteria or contaminants is left on that filter. And we can then use that filter to grow and test for anything that might be apparent there. So we run this and we get 2 different membrane filters. They're exactly the same. We use the same sample for them, but we place them on 2 different types of plates. And we use McConkey agar for this. And we have one McConkey agar plate that has nothing on it. It hasn't been treated. And then we have a McConkey agar plate that has been supplemented with cefotaxime, which is an antibiotic, to look for antibiotic-resistant properties. And we actually do this twice. So for each sample, we would have 2 McConkey agar plates that have no cefotaxime in it, and additionally 2 McConkey agar plates that did. And this is just to make sure that there were no contaminations or things that weren't actually valid for our research. And contaminations could come from a multitude of things, human error, touching something in the lab that you weren't supposed to, and then not properly being sanitized afterwards, or just the agar not being prepared or stored properly could also affect this negatively. So we do multiple runs to make sure that our results are as valid as possible. So after we do membrane filtration, we put them on our McConkey agar plates. We'll incubate these for about 24 to 48 hours, observing the different growth starting around the 24-hour mark, then the 36-hour mark, and then the 48-hour mark. And at the end of this incubation period, we look for any type of growth. And if there is any type of growth on specifically the McConkey agar with cefotaxime supplemented into it on that plate, that shows signs of antibiotic resistance, because whatever bacteria was in that sample was able to grow regardless of the cefotaxime being in its nutrient source. So we will rerun that plate one more time. So one more round of membrane filtration, one more incubation period, just to make sure that that is exactly what we found. And once we get that, we will do a quadrant streak using that sample that has shown signs of antibiotic resistance and isolate one single colony. And we will inoculate a TSB tube with that colony. And then that colony isolated gets frozen and could be used for further research. So one of the tests we used our isolates for was the Kirby-Bauer test. So the Kirby-Bauer test is used to test for multi-drug resistant properties. So we chose 10 antibiotics to test our samples against, and the antibiotics and their classes are listed on the screen. And each antibiotic was in a small disc that was placed on Mulin Hinton 2 agar. And then our TSB isolate was spread out over the agar plate. And the general scheme is that if the antibiotic disc doesn't affect the bacteria, meaning that that bacteria is resistant to that antibiotic, there will be a large clearing around it, showing that the bacteria was still able to do what it wanted to do and use its nutrient source. But if around the antibiotic disc there was no clearing, that means that that specific bacteria was sensitive and susceptible to that antibiotic, and it's not showing signs for antibiotic resistance. So the diameters of the clearings are significant. They show, it's kind of a gradient scale for how they can be affected. They can be completely sensitive and susceptible to an antibiotic, or they could be kind of intermediate, or they could be completely resistant. So by measuring the diameters, we're able to keep track of these on a few hours at a time basis and determine the growth from all of the samples compared to the bacteria. And it's important to note that the only samples we used for the Kirby-Bauer test were samples that tested positive for antibiotic resistance in our pre-screening, which means this bacteria did grow on a cefotaxime supplemented McConkey agar plate. So for results, these results are from the first part of our experiment when we were in the process of getting our isolates. So the first 3 bars show how much out of the 174 samples that we took in total, how many of these samples grew on McConkey agar without cefotaxime supplemented into it. So out of the 174 samples that we collected, overall, only 38 of them grew on McConkey agar, and here they are split up into which counties we found them in. And it's the same process underneath for out of all the 174 samples we collected, only 21 of them grew on McConkey agar with cefotaxime. So overall, 21 out of 174 of our samples, about 12%, showed signs of antibiotic resistance. This next graph is showing all our results from the Kirby-Bauer test. So it's a little bit hard to see because it's in grayscale, but I'll do my best to explain if you guys can see my cursor. So the darker bar, so first over here, we have listed all of the antibiotics that we personally use for our Kirby-Bauer test to test around. And this bar shows the percentage of the isolates tested against that, how many of them were susceptible. So if it's super dark, this shows the percentage out of all our isolates that was susceptible to amoxicillin. And then over this lighter gray bar shows all the percentage of our samples that were resistant to, that were completely resistant to amoxicillin. And then the last part of the percentage is intermediate. Yeah, so we are currently working on speciation in our lab to find out what these species are and if they do pose a public health concern. And the manuscript on this research is in preparation and will be released in the coming weeks. But I just wanted to point out some acknowledgements to all of the amazing people that also work in the lab at the UNC Gillings School of Public Health. All of these people were amazing contributors, and this project wouldn't have happened without them. So thank you.
Thank you so much, Katiana. Let's give Katiana a virtual round of applause. And I'll remind all of our participants to please write your questions into the Pathable chat so I can monitor those. I don't have any questions coming in at the moment, so I will ask you one myself that I have. It looked like, based on county, there was a difference in a number of isolates that were resistant, possibly to cefotaxime. Do you know what some of the exposures of those wells could be in Orange County and also Robeson and Bladen? Were they different? Could there have been different sources nearby?
Yeah, absolutely. So so the reasons these counties were picked actually, so down here, if you can see my cursor, this is Bladen County and Robeson County. I'm not sure which one, I might have them flipped. These were both heavily affected by Hurricane Florence, which is an extreme weather event, which made them a really great candidate for this project. But up here in Orange County, which is around Chapel Hill itself, this is a lower socioeconomic income area. So these private wells tend to not have been taken care of as well and don't receive the proper attention and testing that they maybe should. So that made them a perfect candidate for us to test for antimicrobial resistance.
Thank you. I have a question coming in from Emanuele Sozzi. Once the speciation is completed, what impact do you think this could have in terms of recommendations to possibly be given to the well owners?
Could you repeat that question for me one more time?
Yeah, once you finish the speciation, what impact could that have in terms of the recommendations you might give to the well owners?
Yeah, so having solid data like this makes it a little bit easier to reach out to private well owners and show them the concerns and repercussions of not having regular testing on their private wells. And this could hopefully in turn make them want to start testing their wells more often or consider a different water source if the next time they move somewhere. So just to inform them and give them solid data that they might not have before as what could actually happen if they aren't doing the regulated, the non-regulated testing.
Great. And have you done any laboratory work to determine what sort of organisms these are?
I personally have not. I'm not sure if Lunid or Berkeley are in here right now. Let me see, but I can pass this on to Emmanuel Sosi, who is continuously working on this project for what to do going forward.
Great, thank you so much. Really appreciate your presentation. At this time, I'd like to introduce our second speaker, Anna Libey from the University Colorado Boulder in Colorado, United States. You can start sharing your slides now. Thank you. Great, I can see your slides.
Well, hi everyone, thanks for coming. So my name is Anna Libey. I'm a PhD candidate at CU Boulder, and I'd really first like to recognize my co-authors on this, Pranav Chintalapati, who's also available to answer questions, Professor Bernard Amadei, and Professor Evan Thomas. So first, I'm going to start with defining a maintenance system. This is what we're talking about today. This is the feedback loop of the lifetime of a pump, wearing down, breaking, and then being repaired after a delay, the two double lines there. It's a reinforcing loop. So there's two possible directions or dynamics the system can go in. Either the repairs happen faster than breakdowns and functionality increases over time, or more likely the reverse, as seen in this graph here. Due to the delay, the fundamental dynamic here is that breakdowns are always happening faster than repairs, so functionality declines over time as broken pumps accumulate. Adding on the financial aspect also shows how resources and funding for maintenance is critical. That feedback loop is a balancing one because more repairs equals less money available for future repairs. So our system hypothesis is that most rural water maintenance systems are characterized by periods of rapid growth and then long-term underinvestment. When the maintenance system is stretched beyond its limit, it will compensate by lowering performance standards, which reduces the perceived need for investment in maintenance. It also leads to lower performance, which justifies further underinvestment over time. Therefore, you need a highly leveraged systems intervention to affect how the overall system functions. Our study context is the remote arid regions of Afar in northern Ethiopia and the 5 northern counties in Kenya. Today, I'm mostly presenting on the Afar work. Because of the challenging hydrogeology in this region, the most common type of water scheme in these areas are large mechanized boreholes, many over 100 meters deep and powered by grid power where available, or more commonly, diesel generators or solar panels. The photo on the left is the inside of a pump house with a generator, and is one of the more orderly ones I've seen. Schemes are generally maintained by volunteers or very low-paid pump caretakers, so preventive and regular maintenance is generally not practiced, since they don't have the technical skills or the necessary equipment. Repairs of these schemes are the responsibility of the Regional Water Bureau in Ethiopia and the county water departments in Kenya, since they're outside local capacity. In Afar, almost all of these schemes are also outfitted with sensors, shown on the right, that detect pump runtime and transmit via satellite or cellular networks. The idea is that the regional government can use the sensor reports to respond faster to broken schemes. However, the regional maintenance team is greatly underfunded and functionality rates remain low because they're not able to keep up. So using the sensor data, donors can also learn how the capital investments have fared, hopefully making the case for more funding for maintenance in the future. This is a case I also make in a previous paper I presented on yesterday, the case for water. So today I'm presenting just the model for Afar, but we'll be incorporating all the 5 northern Kenyan counties shown on this map. A primary source of data and understanding about the maintenance systems in this region come from sensor data provided by SweetSense. These graphs on the website show the calculated borehole uptime, which is the time series data used to calibrate the maintenance systems models. And this data is actually publicly accessible, the URL above. And these are the other sources of data that we input into the model. Borehole characteristics and estimated failure and repair rates come from the custom and water asset management platform built for Afar region, the Afar AMS. There are 2 sources of borehole failure and repair reports, manually recorded and sensor reported periods of no use where the pump is possibly broken. So validating all the sensor reports to user submitted site reports was an initial step here. For environmental data, I'm using rainfall from the CHIRPS dataset as a proxy for surface water use to explain seasonal low use of pumps when there's high rainfall. And finally, the O&M team processes and budget are also incorporated because that's the baseline capacity to conduct repairs in the region. The O&M team process and budget is also theorized as a key leverage point for intervention in this system. So this is an example of a little snippet of the model and how I'm using real data from the asset management system and the asset inventories to simulate repair rates. So here, distance to site is a graphical parameter used to calculate the length of time a repair takes, which affects the cost when a vehicle has to be rented for the repair. So taking the GPS coordinates of all the different sites, I calculated the distance that the M-Team office has to drive to reach each site, and then apply distribution to apply to future schemes installed over the 10-year simulation. And the Weibel PDF in this case had the best fit. So these are some preliminary simulation outputs for borehole functionality over a 10-year simulation going to 2026, calibrated to real data from 2017 to today, and then projecting into the future from today until 2026. So the repair rates lag slightly behind breakdown rates, leading to an accumulation of broken pumps over time. Interestingly, major breakdowns are responded to first, while minor breakdowns accumulate due to the higher prioritization of major breakdowns and severity. On the right, the functionality calibration is shown from 2017 to today, where the dots are the real data that we imported into the system. So accounting more accurately for the seasonality and the functionality data has been a challenge, but I'm using differential evolution payoff calibration to get that to fit more closely in the future. And we have here a functionality trend line of about 80%. So this is what the model interface currently looks like, and this is going to be published on the internet where users and stakeholders can go and manually adjust these things themselves. The two key drivers of borehole functionality in the model are pump usage, and therefore how quickly a pump breaks down, measured here in like liters per capita per day of water consumption, and then the usage of each pump per week in hours. And then the budget and allocations for repairs that enable a team to go and fix a pump, where capital expenditure is spending on new construction, direct support, indirect support, that's the monitoring budget, where they find out about borehole runtime. And then O&M and capital maintenance is the repairs budget here. On the graph on the bottom right, the red dots are the real sensor reported functionality levels from 2017 to today, and that's overlaid by the blue line, which is the modeled functionality, which is what I'll be adjusting. So this is a demo of me actually adjusting the interface to show the resulting functionality changes in the 10-year borehole functionality simulation. So first I'm adjusting the breakdown thresholds in hours right now, which is how long it takes before a pump is likely to break down, although some pumps break down sooner or later. The calibrated values in this case are about 3,500 hours for minor maintenance and 40,000 hours or 4.5 years of continuous use, although many pumps break down sooner for major. So when I lower the thresholds and increase the water demand and the pump runtime over time, that actually drops the functionality significantly, like you see in the graph. Okay, so the underlying dynamic in rural water supply is decreasing functionality over time, unless repair rates can essentially outpace the breakdown rates that we see. But it also takes a significant intervention and increased budgets for repairs to overcome some system resistance to change to increase functionality. And then also in this region, borehole usage and water consumption is super low, only about 13 liters per capita per day, and pumps are only run about 50% of the day due to preference for surface water because it's free. So baseline functionality is actually higher than expected originally. And so next steps here are choosing 1 to 3 strategies, which are theoretical maintenance policy interventions to adjust the system towards a reasonable prediction for the financial implications for functionality. And I'd also really like to acknowledge my partners here with USAID, the Sustainable Wash Systems Learning Partnership, and then USAID Kenya Rapid also for the Kenya part of this. And I'm ready to take any questions.
Thank you so much, Anna Libey. Let's give Anna a virtual round of applause. Thank you for your presentation. I'll remind all participants that if you would like to ask any questions, please put them into the Pathable chat so that I can direct them to Anna. Great, we have Sarah Young says, fantastic presentation, Anna. Good job. I'll ask a question as I don't have any coming in at this moment. Do you have any ways that you plan to communicate this outside of the normal scientific paths?
Yeah, so something planned in our region is a regional maintenance strategy workshop with our partner there, IRC. And so they're going to bring some government officials together to discuss maintenance policy strategies that they've seen work in other places. And I hope that model outputs from this can actually be sufficiently accurate that we could potentially model some strategy simulations directly. But that's upcoming work. So.
Great, thank you. Well, I don't have any, oh, here we go, from Erin Bivens. How are you thinking to incorporate the seasonality into the models?
Yeah, so I think I need to have some better data on budget allocations, because right now the first of the year is when the budget hits, and then it does get kind of spent all at once. So there's also kind of like a cyclical part of the functionality there, but it doesn't always quite line up with the rainy season the way I thought it would. So having better data on budget allocations, and then also maybe directly on surface water would be really good to have in this case, because rainfall is not quite as accurate.
Interesting. Thank you. Erin Bivens says thank you as well. Okay, I don't see any more questions coming in, but if you want to monitor the Pathable chat, if anybody thinks of another question, you're welcome to ask that there, and Anna can respond in the Pathable chat or directly through direct messaging. So at this time, I would like to invite our third speaker, Dr. Marian Santoso from Northwestern University in the United States. If you could share your screen, please. Great, I can see your slides.
Unmuted.
There we go.
There we go. Yeah, good afternoon. Thank you again for the opportunity to present at this prestigious conference. My name is Marian Santoso, and I'm an Imana Research Fellow from the Department of Anthropology from Northwestern University. My co-authors, Josh Miller, Hannah Powell, and especially our PI, Dr. Sarah Young, are in the chats and can help answer some of your questions. We also want to take the time to thank USAID for providing us with the funding for this analysis. So let's start with the fact that water is fundamental for agriculture. Agriculture is the largest user of water globally. Over 70% of fresh water is used for agriculture. This relationship between water and food security is more crucial than ever, given that one, increase in due to climate change and increased demand on agriculture. Global food production must increase by nearly 50% by 2050 to keep up with the growing population and dietary changes. These global challenges are especially devastating for smallholder farmers in many low and middle income countries. While exact definition varies, two characteristics of smallholder farmers are one, limited access to agricultural assets such as land and water, and two, high dependency on farming results as income. This makes them especially vulnerable to variation in rainfall and other aspects of water insecurity. It is also worth noting that there are a significant portion of the population. For example, in Asia and Africa, an estimated 1.5 billion people live in smallholder farming households, and they produce 80% of the food supply. However, when we do the search on water and agriculture, we only found studies that use data on the global, national, and subnational level. Or if we find studies on the household level, it is only focused on water availability, which is a critical component of water insecurity, but misses other essential experiences, particularly those associated with water accessibility, use, and stability across time. This means that there is a lack of data on household experiences of agriculture water insecurity. There is one initiative that tried to measure our experiences in water security, like some of you might be aware of. It's called HY Study. In 2017 and 18, about 7,000 households from 24 sites were interviewed on various types of experiences of water insecurity to identify a scale that is valid globally. After lots and lots of interviews and statistics, they came up with a 12-item scale that functioned equivalently across low and middle income countries. The scale took about 3 minutes to administer, and the questions vary from whether a household be worried about not having enough water to having no drinkable water whatsoever in their household for the past 24 hours. Recently, yesterday, a short 4-question version of the scale has also been published. With this new scale, we are now able to do many things to include a better assessing prevalence of water insecurity, such that the scale is now included in the Gallup Whirlpool in Sub-Saharan Africa and India. Better understand consequences of water insecurity, including their syndemic effects along food insecurity on women's depression, and as the mediating variable between water governance and well-being. And lastly, monitor and evaluate various interventions. However, if you notice, experiences in agriculture water security were not part of the 12 items that made it to the final scale. 2 agriculture-related questions were actually part of the questions that was explored in the initial study, but did not make it to the final 12 since agriculture is not a universal experience. However, since agriculture is actually a central experience for a substantial part of the population, we want to explore these 2 questions further. Specifically, we want to understand the prevalence of and severity of household agriculture water insecurity and its correlation with food insecurity. Since we know the standard HY scale is correlated with food insecurity, as seen in this analysis, we are also analyzing their interaction. So first, we explore the prevalence and severity. Since there's 2 questions in HY's Ag, and each question scored from 0 for never and 3 for always, HY's Ag score ranges from 0 to 6. In this graph, I will show the proportion of household in rural and urban and peri-urban areas that answer that the questions are not applicable, which means that they own neither crop nor livestock, that they own crop and livestock but have no problem with household agriculture water insecurity, that they have low household agriculture water insecurity, or that they have high household agriculture water insecurity. First thing to point out is that almost half households in urban and peri-urban areas report that they don't farm and therefore have no answer for these questions. This is not surprising, we know this. But this is why for the rest of the presentation, I will focus on results from rural households. Next thing to notice is that over half of the respondents who answered this question said that they don't have problem with household agriculture water insecurity. Finally, about equal proportion of the rest were experiencing low or high household water insecurity in agriculture. Now we explore the HY's Act's relationship with food insecurity and their interaction with the full HY scale. For all 3 analyses under this section, I will present them in regression table and graphically. Okay, so let's consider the graph. As you can see, if you're on the bottom left of the graph, that means you're feeling secure about both of your food and water situation, so you're smiling. And if you're on the top right of the graph, that means you're not feeling secure about your food and water situation, and therefore you're not smiling. Now, as you can recall, there is a correlation between the original HY scale with food insecurity, which means as you're getting more secure with food water situation, the more secure you are with your food situation. Now let's do the same analysis with HY's Ag. Same thing, happy face if you're secure with both, sad face if you're not secure with both. We also found positive correlation between household agriculture water insecurity with food insecurity, even though the overall magnitude might not be as pronounced as the original 12-item scale. Now, when we analyze both the original HY scale and the HY's Act module on the relationship with food insecurity, we found a negative interaction term. What does that mean? Let's go to the graph. If you're feeling secure about your household agriculture water, the relationship between the original HY scale and food insecurity looks like this blue line over here. What if you have low household insecurity in agriculture? So let's see the green line. There's also that correlation, but the effect is smaller. This continues if you have high household agriculture water insecurity. The yellow line shows that this effect is even smaller, almost flat. What does this mean in real life? This means both HY's and HY's Acts, while positively correlated with food insecurity, but their impact together is less than the sum of their individual impacts. This might indicate a limit of impact of water insecurity experiences, agriculture or otherwise, on food insecurity. It is worth noting, however, that AIC and BIC indicates that including HY's Act in our analysis explain more variation in food insecurity. Moreover, it is also worth noting that a household that felt secure in their overall household water, but not in agriculture, would still have a high expected food insecurity. Please note that this analysis is only the first step in understanding of household agriculture water insecurity experiences. For immediate future research topics, we recommend the following. First, geographical variations. When we analyze the interaction above by site, the relationship vary. We cannot say anything definite since our sample is not representative for any specific geographical locations, but more analysis to see how this relationship vary by population needs to happen. Second is pathways. More analysis needs to be done on understanding how a household agriculture water insecurity impacts food insecurity. For example, is it simply due to its correlation with agricultural yield, or does it dictate farmer decisions such as choosing crops that are drought resistant instead of high yielding? Another possible heterogeneity in this relationship is the level of household dependence on the agricultural result. Access to market might mean that a household is less reliant on their own food production, and therefore the relationship between household agriculture water insecurity and food insecurity then therefore would be also less. Next is time of the year. This analysis used water and food insecurity from the same time point of the year. However, one can easily imagine how water insecurity during the growing season would only be relevant to food insecurity in the subsequent post-harvest season. Fifth, annual variation. There's indication that annual variation in the water situation is perceived more readily by participants rather than the absolute amount of water. For example, agriculture season, sites that are used to low rain in the agricultural season reported lower HYS Act than sites that are used to a high amount of rain but had a bad year. Finally, water insecurity experiences is also very gendered. More analysis needs to be done on how male and female respondents from the same household will differentially view their household agriculture water insecurity experiences. So to recap, measuring household experiences in water security is helpful. HYX will allow us to do that for household agriculture specifically. HYX is mostly relevant in rural areas. It helps paint a more complete picture on the relationship between water and household and food insecurity in rural household. Much more analysis needs to be done. And at the end of the day, should I add HYX in your survey? We say yes, especially if you work with farmers. And if you need help with analysis, you can find us here. Thank you.
Thank you so much, Dr. Santoso. Let's give Marianne Santoso a virtual round of applause. Thank you. And I'll remind again all of our participants, if you have any questions, please direct them to the Pathable chat. I'm also going to unmute Dr. Sarah Young, who is also a co-author, to respond to any questions or to add anything that she would like to add as well. I'm not seeing any questions come through the chat at this moment. Can you speak to where you validated this, or if you validated this, or how you have plans to validate this?
Dr. Young.
So that's a great question. We validated the 12 core HYS items in 23 sites, 23 countries, 28 sites in low and middle income countries. We haven't validated the agricultural questions per se. I mean, we've looked at some of the variation in them, but one of the things so they seem to be working, and Vicky led a study in Singida, Tanzania, where it was all smallholder farmers, and it was a useful endeavor there. But one of the sort of interesting and tough questions about asking about water for agricultural practices is what people's expectations are for irrigation. So in some places, of course we irrigate, and we irrigate either through collecting rainwater or natural rainfall or other methods. Some places you could really benefit from irrigation, but it's just not even in people's mind. Like where we were in Singida, people aren't going to irrigate their maize. It's just far-fetched. So what I would encourage myself to do in future studies and others is to understand what the agriculture water expectations are before we ask if you're running short or not.
Thank you. We do have a question coming in from Anna Libey, one of our earlier presenters. The time of year part sounds important. Is there any relationship with delayed rainy seasons and HY scores, especially where we're affected more by climate change, e.g. for rain-fed irrigation?
Yeah, thank you, Anna. Actually, even though we were not able to do that analysis using this data set, in a separate agriculture small forwarder farming household cohort that we have, we actually see this. There's 1 year where the rain was delayed, and that is when we see the highest HYX score. Yeah, but I think it is very important that we collect more data on this more globally and see if this is also relevant. So I think that's also this time of year part connected with the annual variation part. It's in terms of people's expectations.
Yeah, and I would maybe take this opportunity to point out another shortcoming in these data. Nothing, they're my data, I'm criticizing myself. These are cross-sectional data for the most part. And in Kenya, that's the only place I know of where we have food insecurity and water insecurity, household water insecurity concurrently over time.
Yeah.
And that's the first evidence of a causal relationship between water insecurity and then subsequent food insecurity. And in using structural equation modeling, we showed that there is indeed that relationship. So that's only one study in one place, but it really suggests the plausibility of a causal relationship.
Very interesting. Thank you so much. Our time has run out for our, well, we have one more question, so I'm just going to ask it. This is from Aaron Bivens. Any plans to use this tool in India, or has it been used there? Farmers in Maharashtra, apologies for the mispronunciation, are often under extreme duress when the monsoon is late or inadequate.
Oh, okay. Sarah is present, so I'll just answer. Yes-ish. We need to. There are some plans, and it's actually, as we mentioned, the HY scale is also in the Gallup borehole. But I think if you have connection, if you have projects in India who can, where we can ask this to question, I think that'll be great. I'm not aware of the specific plans so far. If there's any connection, but if you have any ideas of a project who can use this, let's talk.
Great, thank you. And so with that, I'll close our session. I just want to say thank you again to our three speakers, Katiana, DeYonke, Anna Libey, and Dr. Marian Santoso. Thank you much. And thank you to all of our participants. And I hope you have a good rest of your morning, evening, day. Join us for trivia in a couple of hours. And I will now be ending this session.
Thank you.